Look up at the night sky on a clear evening, and you might catch a glimpse of it, a brilliant, steady point of light, shining with a pale golden glow. That distant beacon is Jupiter, the king of our solar system, a world so immense that all the other planets could fit inside it with room to spare. But Jupiter is more than just a pretty sight or an astronomical record holder. It's a living, breathing mystery, wrapped in bands of swirling clouds and illuminated by storms larger than our entire planet. For centuries, we've gazed at this giant, wondering what secrets it holds deep within its turbulent atmosphere. What forces are at work beneath those magnificent, colorful stripes? What strange, unseen phenomena shape its wild and stormy character? From its great red spot, a hurricane that has raged for at least 400 years, to its powerful magnetic field that could swallow worlds, Jupiter challenges everything we think we know about planets. It's a place where conditions are so extreme, so alien, that they defy easy explanation. And with every mission we send, from Voyager to Juno, we uncover not just answers but deeper, more fascinating questions. This is a world that seems to guard its truths jealously, revealing just enough to keep us hungry for more. It invites us into a story of discovery that spans generations, touching on our deepest curiosities about where we come from and what lies beyond our own world. So join us as we embark on a journey to explore 25 of the most compelling, strangest, and most awe-inspiring mysteries of Jupiter. We'll venture into the heart of its endless storms, dive beneath its cloud tops into realms of crushing pressure and exotic matter, and unravel the puzzles of its moon's worlds with hidden oceans and volcanic fireworks. This is more than a list. It's an invitation to wonder, to question, and to marvel at one of the most complex and magnificent objects in our cosmic neighborhood. What we find might just change how you see the night sky forever. And so we arrive at our first and perhaps greatest mystery, a tempest so vast it has become the very face of Jupiter itself, the Great Red Spot. For centuries, telescopes have revealed this swirling, brick-red vortex in the planet's southern hemisphere, a colossal hurricane that could easily swallow our entire planet whole. But its immense size is only half the story. Its true enigma lies in its staggering longevity. This storm has been churning non-stop for at least 400 years since astronomers first laid eyes on it in the 1600s, and it was likely raging for centuries before that. This simple fact shatters our understanding of planetary weather. On Earth, even the most powerful hurricanes draw their energy from warm ocean waters and dissipate within weeks once they move over land or into cooler areas. They are fleeting phenomena. Jupiter has no solid surface to break up a storm, but according to every atmospheric model we have, the turbulence and sheer forces within those violent cloud bands should have torn the Great Red Spot apart long ago. The sheer friction alone should have caused it to sputter out centuries ago. Yet there it is, a perpetual marvel of meteorological defiance. So what is the secret to its endless energy? What cosmic engine keeps this ancient storm alive? Scientists are piecing together several compelling theories. One leading idea suggests the storm is somehow drawing up heat from the deep interior of Jupiter itself. Unlike Earth, which is warmed primarily by the sun, Jupiter radiates more heat than it receives, a leftover bounty from its violent formation. This internal furnace may be providing a constant infusion of thermal energy, rising through the atmosphere to fuel the spot's fury. Another fascinating theory points to the storm's ability to consume smaller vortices. Like a planetary-scale predator, the Great Red Spot has been observed absorbing smaller storms that wander too close, cannibalizing their energy and momentum to sustain its own existence. It's a relentless cycle that has allowed it to weather the ages, but perhaps the most intriguing puzzle of all is its recent transformation. In recent decades, our observations have shown the spot is actually changing shape. It's becoming more circular and, by some measurements, possibly even shrinking. This has led to intense debate among planetary scientists. Is this the beginning of a slow, final demise for this legendary storm, or merely another phase in its incredibly long life? Is it shrinking in mass or just condensing? The Great Red Spot offers no easy answers, only a deeper mystery. It stands as a monumental reminder that for all our knowledge, the universe still holds phenomena of such immense power and duration that they challenge the very frameworks we use to understand our world. While the Great Red Spot presents a visible, atmospheric puzzle, our next mystery takes us deep beneath those cloud tops into the very heart of the planet itself. For generations, the prevailing model of Jupiter's interior was a rather straightforward layered affair. Scientists envisioned a dense, compact core of rock and ice, a relic from the planet's formation, wrapped in a deep mantle of metallic hydrogen, all enclosed by the outer layers of liquid and gaseous hydrogen that we see as its atmosphere. This solid core was considered the seed around which the gas giant had coalesced, a foundational anchor in the violent early solar system. But then the Juno mission arrived, and its precise measurements of Jupiter's gravitational field delivered a shocking revelation that turned this textbook picture completely upside down. The data suggests that instead of a small, sharp, and solid mass at the center, Jupiter's core is fuzzy or diluted. It appears to be a vast, partially dissolved boundary that blends gradually into the surrounding metallic hydrogen envelope, stretching across perhaps half of the planet's radius. Imagine expecting a distinct, dense pebble at the center of a ball of gas, but instead finding a diffuse, gargantuan cloud of material that slowly thins out. That's the bewildering reality Juno uncovered. This bizarre structure challenges some of our most fundamental ideas about how not just Jupiter, but all gas giants and even planets in general are born. How could such a massive, seemingly eroded core come to be? Planetary scientists are wrestling with two compelling, yet dramatically different hypotheses. The first is a story of colossal violence. Early in the solar system's history, a planetary embryo still in its formative stages may have slammed directly into a young, still-forming Jupiter. This impactor, potentially many times the mass of Earth, would have delivered an almost unimaginable amount of energy, shredding and vaporizing the original compact core and mixing its heavy elements upward into the inner mantle. The second theory is one of relentless internal erosion. It posits that over billions of years, the intense pressures and temperatures at Jupiter's heart could have dissolved the rocky material of the core, causing it to mix and dilute into the fluid metallic hydrogen ocean surrounding it. It's a slow-motion melting process on a planetary scale. Whichever scenario is correct, the implications ripple far beyond our solar system. Thousands of exoplanets we've discovered are gas giants, many orbiting perilously close to their stars as hot Jupiters. If a giant planet's core can be so easily disrupted or dissolved, it forces us to completely re-evaluate their internal structure, their magnetic fields, and their evolutionary history. Jupiter's fuzzy core isn't just a curious anomaly. It's a fundamental clue that we are still missing a major piece of the puzzle of how planetary systems assemble themselves. It shows us that even the most basic building blocks of a world can be transformed by processes we are only beginning to comprehend. Moving from the hidden depths of Jupiter's core, we now turn to one of its most spectacular and visible displays, a light show of such immense power that it completely redefines what an aurora can be. Here on Earth, we cherish the fleeting, dancing curtains of the northern and southern lights, phenomena triggered when charged particles from the sun ride down our planet's magnetic field lines and collide with atoms in the upper atmosphere. They are a beautiful side effect of solar activity, but on Jupiter, the auroras are something else entirely. They are permanent, blazing crowns of light circling the planet's poles, hundreds of times more energetic than our own and radiating enough power to briefly outshine the sun. This isn't a seasonal display, it's a constant raging inferno in the sky, and its energy source has long been one of the planet's most captivating puzzles. The sheer scale is almost impossible to grasp. While Earth's auroras might be visible from space as delicate, shimmering rings, Jupiter's are vast, swirling hurricanes of ultraviolet and X-ray light, each one larger than our entire planet. They are so intense that they heat the upper atmosphere around the poles to temperatures hotter than the surface of the Sun. For decades, the assumption was that, like on Earth, the solar wind must be the primary driver. But the Juno spacecraft's measurements delivered a stunning revelation. While the solar wind does play a role in shaping them, Jupiter's auroras persist with undiminished ferocity even when the Sun is calm. This pointed to a powerful, internal engine, a generator within Jupiter itself, that is capable of producing its own vast currents of charged particles. The leading suspect in this cosmic mystery is Jupiter's own rapid rotation and its incredibly strong magnetic field. The planet spins so fast that a day on Jupiter lasts just under 10 hours. This whirlwind spin, combined with the gravitational pull of its largest moon, Io, creates a truly astonishing dynamic. Io is the most volcanically active body in the solar system, and its eruptions constantly spew massive amounts of sulfur and oxygen ions out into space. Jupiter's magnetic field captures this material, whipping it around at tremendous speeds and creating a vast, donut-shaped cloud of plasma that encircles the planet. This churning, charged particle reservoir is known as the Io plasma torus. It's from this torus that scientists believe the real auroral magic happens. The theory is that Jupiter's own rotation, acting like a colossal cosmic generator, pulls currents from this plasma cloud down magnetic field lines and directly into the polar regions. It's a self-sustaining circuit of incredible power, a planetary-scale electrical dynamo that runs on spin and volcanic exhaust. Yet, even this elegant explanation may not be the complete story. Recent observations of the auroras have revealed features and pulses of energy that don't perfectly fit the existing models. There seem to be secondary processes, perhaps related to other moons or unknown interactions within Jupiter's own magnetosphere, that contribute to the chaos. The auroras are a brilliant signature of a complex system we are only beginning to map, a constant reminder that Jupiter operates on a level of energy and power that we are still struggling to fully comprehend. Yet for all the staggering power of its auroras and the puzzling nature of its core, one of the most fundamental mysteries about Jupiter has long been a question that sounds deceptively simple: just how wet is it? Water, or more specifically, the abundance of oxygen locked within water molecules, is a crucial piece of the puzzle for understanding how this giant planet formed. The leading theory of planetary formation, known as the core accretion model, suggests that Jupiter acted as the solar system's gravitational vacuum cleaner, sweeping up vast amounts of ice-rich planetesimals from the cold outer regions of the primordial solar nebula. If this is true, then Jupiter's deep atmosphere should be rich with water, and this water should be relatively well mixed and uniform. For decades, our best estimates were based on the Galileo probe, which plunged into a very specific, and as we now know, very unusual, location on the planet in 1995. That single data point suggested a startlingly dry atmosphere, a finding that threw the formation models into doubt and left scientists scratching their heads for over 20 years. The arrival of the Juno spacecraft promised to finally deliver a global answer. Equipped with a sophisticated microwave radiometer, Juno was designed to peer deep below the visible cloud tops to measure water abundance at various depths and across many latitudes. The results, however, were not the clear, uniform answer everyone expected. Instead, they revealed a world of perplexing contradictions. Juno found that water abundance is not uniform at all. It varies dramatically from region to region, creating a bizarre patchwork quilt of dryness and relative saturation. In the equatorial region where the Galileo probe made its fateful descent, water makes up about 0.025% of the atmosphere, incredibly arid, more akin to the sun's composition than a water-rich world. But move toward the poles and the story changes completely. The North Polar cyclone, a massive swirling storm system, was found to be rich with water, containing oxygen at levels many times greater than at the equator. This bizarre inconsistency presents a monumental challenge. Our models of planetary atmospheres, especially those of gas giants, rely on the principle of convection, the idea that rising and falling columns of gas should thoroughly mix the atmosphere's constituents over billions of years. Jupiter's fast rotation and powerful weather systems should act like a colossal blender, homogenizing everything within it. The fact that such stark differences in a key compound like water can persist right next to each other suggests that our understanding of atmospheric dynamics on this scale is profoundly incomplete. It implies the existence of unknown processes that are somehow segregating these molecules, preventing them from mixing as our physics says they should. Perhaps powerful, localized downdrafts are dragging dry air from the upper atmosphere deep into the interior, while upwellings in other areas are carrying moist air upward, creating these permanent wet and dry zones. Beyond the atmospheric puzzle, the water mystery cuts to the very heart of Jupiter's origin story. If the planet is indeed dry overall, it could mean it formed much closer to the Sun, in a warmer part of the nebula where water ice couldn't condense, and then migrated outward to its current position. Alternatively, if it is wetter than we thought, it strengthens the classic core accretion model. Juno's patchy findings suggest the truth is far more complex than either simple scenario. The varying water levels could be a preserved record of the planet's chaotic infancy, a fingerprint of the different types of icy material it gobbled up from various parts of the early solar system. The water isn't just a weather report, it's a chemical fossil, and its uneven distribution is a cryptic message waiting to be decoded, one that could rewrite the story of how not only Jupiter, but all the planets found their place around our star. But if the distribution of water was a surprising puzzle, the next mystery plunges us into the heart of Jupiter's most powerful and invisible force. Every schoolchild learns that our Earth has a north and south magnetic pole, creating the familiar field that guides our compasses and protects us from solar radiation. We picture this field as symmetrical, like a giant bar magnet running through the planet's center. Jupiter, true to its nature, completely shatters this simple model. Data from the Juno mission revealed that the gas giant's magnetic field is profoundly and bizarrely lopsided. It's a chaotic, patchy, and deeply asymmetric field, with its northern hemisphere boasting a concentrated, powerful region nicknamed the Great Blue Spot, while the southern hemisphere's field is significantly weaker and more diffuse. This isn't the clean, orderly field of a textbook diagram. It's a tangled, messy, and wildly uneven magnetic tapestry. This profound asymmetry is a direct window into the churning, exotic engine deep within the planet. Scientists believe Jupiter's magnetic field is generated by a dynamo effect, much like Earth's, but operating under conditions we can barely imagine. Our planet's field is thought to be created by the convection of molten iron in its outer core. Jupiter's dynamo, however, is believed to occur within a vast ocean of metallic hydrogen, a form of hydrogen under such immense pressure that it behaves like a liquid metal capable of conducting electricity. The key to the mystery lies in the dynamics of this strange fluid. The lopsided nature of the field suggests that this dynamo is not operating uniformly across the planet. It's likely much closer to the cloud tops than previously assumed, and it may be driven by a complex combination of factors, including the planet's incredibly fast rotation, intense internal heat rising from the interior, and the mind-boggling physics of hydrogen under millions of times Earth's atmospheric pressure. One compelling theory points to the precipitation of helium rain deep within the planet. As hydrogen is compressed into its metallic state, it's possible that helium, which does not dissolve easily in this exotic soup, condenses into droplets and falls inward like rain. This process could be creating localized turmoil, stirring the metallic hydrogen ocean in uneven ways and disrupting the symmetry of the dynamo. The stronger magnetic field in the north might indicate a region where this internal rainfall is less prevalent, allowing for a more stable and powerful convective flow, while the south could be experiencing more of this turbulent precipitation, dampening the field's strength. Alternatively, the fuzzy, diluted core we discussed earlier could be playing a starring role. Its irregular, partially dissolved structure might be interacting with the dynamo region in a way that distorts the magnetic field from its very source, creating these permanent imbalances. This magnetic weirdness isn't just an academic curiosity. It has real and dramatic consequences for the entire Jovian system. This lopsided field directly influences the immense radiation belts that surround Jupiter, creating regions where charged particles are trapped with vastly different intensities. This asymmetry even affects the auroras, contributing to their chaotic and unpredictable patterns. Understanding this magnetic puzzle is crucial because it forces us to rewrite the physics of planetary dynamos. It shows us that these cosmic generators can operate in far more complex and localized ways than our simplest models suggest. Jupiter's messy magnetic field is a humbling reminder that deep within the gas giant, the rules of physics are being written in a language of extreme pressure and exotic matter that we are only just beginning to translate. If the striking unevenness of its magnetic field reveals a chaotic interior, then this next mystery points to the fiery engine that powers it all. Every planet with an atmosphere has an energy budget, a balance between the heat it absorbs from the sun and the heat it radiates back into space. For a world like Earth, that balance is fairly straightforward. The vast majority of the energy driving our weather and climate comes directly from sunlight. Jupiter, however, defies this basic accounting. Despite being over 5 times farther from the sun than we are, receiving only a tiny fraction of the solar radiation that bathes our world, the giant planet glows with an intense thermal radiation. It emits nearly twice as much heat as it absorbs. This means there is a colossal source of energy within Jupiter itself, an internal furnace blazing away in the perpetual cold of space, and the nature of this powerhouse has been a subject of intense debate for decades. This excess heat isn't just a minor anomaly, it is the fundamental driver of Jupiter's spectacular and violent weather. It provides the thermal energy that churns those massive cloud bands, fuels the endless cyclones at the poles, and sustains millennia-old storms like the Great Red Spot. Without this internal heat source, Jupiter's atmosphere would be a much calmer, more subdued place. The leading explanation for this energy surplus has long been a process known as the Kelvin-Helmholtz mechanism. This is a fancy term for a simple concept, the slow gravitational contraction of the planet. The idea is that Jupiter is still very gradually shrinking under its own immense weight. As it contracts, gravitational potential energy is converted into thermal energy, heating the interior. Think of it like repeatedly squeezing a stress ball. The compression generates heat. This process is a leftover from the planet's formation over 4.5 billion years ago, and models suggested this slow squeeze could account for the observed heat flow. But as our measurements have become more precise, this neat explanation has begun to unravel. The amount of heat being radiated is so immense that simple gravitational contraction may not be sufficient to explain it all, at least not at Jupiter's current age and size. This has forced scientists to look for other bank accounts to draw from within the planet's energy portfolio. One compelling theory involves the precipitation of helium we touched on earlier. As this denser helium rains down through the liquid metallic hydrogen interior, it releases gravitational energy through friction, effectively heating the surrounding material like countless tiny meteorites burning up in an atmosphere. This could provide a significant and ongoing secondary source of internal warmth. Another possibility points to the planet's primordial formation. When Jupiter coalesced, it accreted an incredible amount of mass in a relatively short period. The energy from countless impacts of planetesimals and asteroids would have heated the young planet to tremendous temperatures. It's possible that Jupiter is still, in a very real sense, cooling down from its own violent birth, radiating that ancient trauma as heat over billions of years. There's even a speculative theory about the potential for limited fusion reactions deep within its core, where the pressures are so extreme that certain isotopes of hydrogen could be forced together, releasing energy. However, most scientists consider this highly unlikely, as Jupiter is far too small to achieve the sustained fusion that powers a star. The truth is, no single theory perfectly fits all the data. It is likely a combination of these processes: ongoing contraction, helium rainfall, and primordial heat, all contributing to the total, but the precise proportions remain unknown. This energy surplus is more than just a thermal curiosity. It is a direct probe into the planet's composition, its evolutionary history, and the very conditions within its hidden interior. By studying the heat Jupiter gives off, we are essentially taking its temperature, and that feverish reading tells us that the king of planets is still a dynamic, evolving world, burning with the secrets of its formation and the slow, powerful processes that continue to shape it from within. Leaving behind the enigmatic forces deep within Jupiter, we now turn our gaze to its poles to witness one of the most visually stunning and puzzling arrangements in the entire solar system. Before the Juno mission, we had never truly seen Jupiter's poles. Our view was always limited to its equatorial regions, its striped banding and famous Great Red Spot. But when Juno's orbit carried it directly over the North and South Poles for the first time, it revealed a sight that left planetary scientists in a state of pure astonishment. There, perfectly arranged in bizarre geometric formations, were clusters of massive, permanent cyclones. At the North Pole, 8 colossal storms, each nearly as wide as the continental United States, were locked in a precise octagon around a single central cyclone. At the South Pole, the arrangement was a perfect pentagon of 5 equally gigantic storms circling one central vortex. These were not temporary weather patterns. They were permanent, stable fixtures, enduring across years of observation without ever breaking their flawless polygonal dance. This discovery immediately presented a profound mystery. On Earth, and in every fluid dynamics model we have, cyclones are inherently unstable. When they get close to one another, they either merge into a single, larger storm or tear each other apart through a process called binary interaction. They are loners, not neighbors. Yet here on Jupiter, we see multiple hurricanes of unbelievable ferocity, with winds estimated at up to 220 miles per hour, existing in incredibly close proximity, seemingly defying the fundamental laws that govern atmospheric behavior everywhere else. They don't drift into one another, they don't cannibalize each other's energy. Instead, they maintain a perfect, respectful distance, tracing the edges of an invisible geometric shape as if trapped in a celestial waltz. The question is simple yet baffling. What unseen force is acting as the cosmic traffic cop, preventing these monstrous storms from colliding? Scientists are piecing together a fascinating and multi-layered explanation that may involve the unique physics of Jupiter's deep atmosphere. One leading theory points to the powerful Coriolis effect generated by the planet's incredibly fast rotation. This force, which deflects moving objects to the right in the northern hemisphere and to the left in the south, is immensely stronger on Jupiter than on Earth. It's possible that this powerful deflection is creating a kind of protective barrier or anticyclonic ring around each cyclone, a zone of high pressure that acts like a cushion, pushing the storms apart and maintaining their separation. Another compelling idea delves into the role of the deep, internal heat we just discussed. The constant upwelling of warm gas from Jupiter's interior may be providing each cyclone with its own independent energy source, like individual boilers on a stovetop. This could prevent them from needing to compete for fuel, allowing them to coexist peacefully as long as each has its own sustainable heat supply. But the most captivating hypothesis involves the staggering depth of these weather systems. Unlike Earth storms, which are largely confined to the troposphere, Juno's data suggests Jupiter's polar cyclones might be rooted incredibly deep, perhaps extending down hundreds of miles below the visible cloud tops. This profound depth could anchor them in place, making them behave less like superficial swirls on an ocean surface and more like permanent structures carved into the planet's very fabric. Their stability might be a function of this deep anchoring, combined with the powerful rotational forces and the unique energy dynamics of the polar environment. The geometric patterns themselves could be an emergent property of these deep-rooted vortices interacting within the constrained space of the pole, naturally settling into the most stable, energy-efficient configuration, much like bubbles packing together in a foam. Yet, for all these brilliant theories, the precise mechanism remains an active and thrilling area of research. A beautiful puzzle written in clouds and wind on a scale so vast it challenges our very understanding of what weather can be. And yet, even as we marvel at the orderly chaos of Jupiter's polar cyclones, we must turn our attention to one of its most subtle and ethereal features, a feature so faint it went completely undiscovered until the late 1970s. When we think of planetary rings, our minds immediately picture the breathtaking, icy brilliance of Saturn's iconic bands. Jupiter, by comparison, wears a far more delicate and mysterious set of rings, a wispy halo of dust that seems almost ghostly against the planet's overwhelming presence. These rings are so tenuous that if you were to gather all their material into a single blob, it would likely form a moon no more than a few kilometers across. Their very existence is a profound puzzle because Jupiter is, by its nature, a ring-destroying machine. Its immense gravity should act like a cosmic vacuum, pulling in stray dust particles. Its powerful radiation belt should electrically charge those particles and push them out of orbit. So how does this delicate, dusty necklace not only exist but persist? The answer lies not with the planet itself, but with the silent, sacrificial dance of its four innermost moons. Unlike the spectacular water-ice rings of Saturn, which are largely pristine and reflective, Jupiter's rings are dark as charcoal. Spectroscopic analysis reveals they are made primarily of very fine, microscopic dust grains, most likely silicate rock. This crucial detail is our first major clue. These aren't chunks of ice, they're fine powder, and they aren't staying in orbit for long. In fact, scientists estimate that individual particles probably only survive in the ring system for a century, or maybe 1,000 years at most before the planet's gravity and radiation expel them. This means the rings cannot be a permanent, ancient structure left over from the planet's formation. They are a fleeting phenomenon, a celestial exhibit that must be constantly replenished by a contemporary source. The rings we see today are not the same rings that were there a millennium ago. They are a continuous, dynamic spray of new material, and the source of that material has been tracked directly to Jupiter's inner moon. The primary suspects are Metis, Adrastea, Amalthea, and Thebe, four small, irregularly shaped moons that orbit perilously close to the planet, well within the main ring system. These moons live in a brutal environment, constantly bombarded by micrometeorites from interplanetary space. Every tiny impact, and there are millions happening all the time, kicks up clouds of dust from their surfaces. Because these moons are so small and have such weak gravity, the ejected dust easily escapes into space, entering orbit around Jupiter. This creates a series of faint, individual dust rings associated with each moon. The main ring, which is the brightest part of the system, is believed to be sourced primarily from Metis and Adrastea. Farther out, two much fainter and vastly larger rings, known as the gossamer rings for their incredible faintness, are supplied by Amalthea and Thebe. It's a beautiful, self-sustaining cycle. Constant bombardment creates dust which forms temporary rings which are then slowly destroyed, only to be replaced by new dust from the next round of impact. But this explanation, while elegant, opens up new layers of mystery. Why do these rings have such sharp, well-defined boundaries? The outer edge of the main ring, for instance, is abruptly cut off right at the orbit of Adrastea. This suggests the Moon is not just a source but also a shepherd, its gravity neatly confining the ring particles and preventing them from drifting outward. Furthermore, data from the Galileo spacecraft hinted at a population of larger, boulder-sized objects embedded within the rings that we cannot see directly. These unseen bodies might be the parent objects that generate the fine dust through their own collisions, acting as hidden engines for the entire system. The greatest lingering question, however, is one of history. Is this the ring system's permanent state, or has it changed dramatically over billions of years? A major collision between two moons in the distant past could have created a much more massive ring that has since decayed to the wispy structure we see today. The current dust generation mechanism might simply be the quiet, steady state of an aging system. Jupiter faint rings are a masterpiece of balance, a delicate equilibrium between creation and destruction, reminding us that even the most subtle features in our solar system can hold profound stories of gravity, impact, and resilience. Perhaps no feature defines Jupiter's majestic appearance more than its stunning banded structure, those alternating dark belts and light zones that wrap around the planet like a finely crafted celestial tapestry. For centuries, these stripes have been the most prominent feature visible through telescopes, creating the iconic look of a world painted with bold, parallel brushstrokes. But unlike a static painting, Jupiter's atmosphere is a living, breathing entity, and these bands are in a constant state of dramatic, unpredictable flux. They are not permanent features, they are colossal weather systems, each one a fast-moving river of gas thousands of miles wide, and their behavior is one of the planet's most enduring meteorological mysteries. The bands can fade, darken, or change color entirely. Most bizarrely, entire sections of this striped pattern have been known to vanish for years at a time, only to reassert themselves later as if nothing had happened, leaving astronomers to wonder what powerful, unseen forces are orchestrating these planetary-scale makeovers. To understand the puzzle, we first need to know what these belts and zones actually are. The lighter-colored zones are regions of rising air where ammonia ice clouds are pushed up to higher, colder altitudes, making them appear bright. The darker belts, on the other hand, are areas of sinking air where the atmosphere is descending and clearing out the upper cloud layers, allowing us to see deeper into warmer, darker atmospheric regions. This creates a massive planet-wide conveyor belt of circulation, with air rising in the zones, moving laterally, and sinking back down in the belts, all driven by Jupiter's tremendous internal heat. For a long time, it was thought this was a relatively stable, predictable system, but observations have shown it is anything but. The most famous example of this chaotic behavior is the sudden and complete disappearance of the South Equatorial Belt, one of the two most prominent dark bands flanking the equator. Approximately every decade or so, this massive dark feature simply fades from view, leaving the equatorial zone as a brilliant, uninterrupted white band for a period of months or even years. Then, just as mysteriously, it begins to re-emerge. It often starts as a single, brilliant white plume erupting within the zone, which then darkens and spreads out, eventually re-establishing the entire belt. This isn't a subtle change, it's a total transformation of one of the planet's most defining features, and it happens on a scale so vast it's visible from backyard telescopes on Earth. So what triggers this planetary-scale vanishing act? The leading theory involves a complex interplay between chemistry and dynamics deep within the atmosphere. The prevailing idea is that the dark belts are not actually disappearing, they are being hidden. Scientists believe the dark coloration is caused by compounds called chromophores, which are likely complex sulfur or phosphorus compounds or perhaps complex hydrocarbons that form when the deeper, warmer air is exposed to sunlight. The theory suggests that during these fading events, powerful, bright white ammonia ice clouds from the neighboring zones billow over and obscure the darker belt material, effectively creating a brilliant blanket that hides the belt from view. Eventually, powerful convective upwellings from the deep atmosphere punch through this cloud deck, bringing the dark chromophores back to the surface and restarting the cycle. It's a planetary game of peek-a-boo played out over years, with the atmosphere itself acting as the curtain. But this only explains the mechanics, not the trigger. Why does this happen on such a regular yet unpredictable schedule? The answer likely lies in the complex feedback loops between the planet's internal heat flow, its chemistry, and its powerful jet streams. Small perturbations in the upwelling of heat from the interior could alter the stability of the cloud decks. Alternatively, waves propagating through the atmosphere from giant storms or other disturbances could disrupt the delicate balance, initiating a chain reaction that leads to the obscuration of an entire belt. The recent observation of similar, though less dramatic, color changes and fadings in other belts suggests this is a fundamental property of Jupiter's atmospheric engine, a rhythm of change and renewal written into the very fabric of the planet. These shifting stripes are a powerful reminder that Jupiter is not a serene, static giant, but a dynamic and moody world, its face constantly remade by the churning, hidden forces operating deep within its atmosphere. Delving deep beneath the turbulent cloud tops and intricate weather patterns, we encounter a substance so exotic that it defies our everyday experience of matter, a vast, churning ocean of liquid metallic hydrogen. This isn't science fiction, it's the predicted state of hydrogen under the mind-boggling pressures found within Jupiter, and it represents one of the most fundamental mysteries of the planet's interior. To understand the conditions there, we need to grasp the sheer scale of the pressure. As you descend through thousands of miles of hydrogen gas, the weight of the atmosphere above you grows exponentially. Around 10 to 15,000 miles down, the pressure soars to millions of times greater than the atmospheric pressure at Earth's surface. Under this incredible crush, the very nature of hydrogen undergoes a radical transformation. Here, the familiar rules of chemistry break down. Under normal conditions, hydrogen is a transparent gas, its molecules bouncing around independently. At the depths within Jupiter, the immense pressure forces the atoms so close together that their electrons are no longer bound to individual protons. Instead, they break free, creating a soup of positively charged protons swimming in a sea of negatively charged delocalized electrons. This is the state known as liquid metallic hydrogen. It behaves like a liquid in that it flows, but it also behaves like a metal because those free electrons can conduct electricity with virtually no resistance, making it a superconductor on a planetary scale. Imagine an ocean of shimmering, molten mirror that is both a fluid and a perfect electrical conductor. This is the bizarre and hypothetical substance that scientists believe makes up the bulk of Jupiter's interior. The existence of this material is central to explaining Jupiter's most powerful feature, its enormous magnetic field. Magnetic fields are generated by dynamos, the convective motion of an electrically conductive fluid. On Earth, this fluid is molten iron swirling in the outer core. On Jupiter, the primary dynamo is thought to be this roiling ocean of liquid metallic hydrogen. The planet's incredibly fast rotation, a day lasting less than 10 hours, whips this conductive fluid into a frenzy, generating powerful electric currents. These currents, in turn, produce the planet's massive and complex magnetic field. It's a self-sustaining generator of epic proportions, and the properties of liquid metallic hydrogen are the key to its incredible power. Without this exotic ocean, Jupiter's magnetic field would be a fraction of its current strength. Yet for all its theoretical importance, liquid metallic hydrogen remains frustratingly out of reach for direct study. It is the holy grail of high-pressure physics, but recreating the conditions found at Jupiter's core, even for a fraction of a second, has proven to be one of science's greatest experimental challenges. On Earth, we can generate immense pressures using diamond anvil cells, which squeeze tiny samples between the pointed tips of two diamonds. Scientists have come close, creating what they believe is a semiconducting state of hydrogen, but achieving the millions of atmospheres of pressure needed to create the truly metallic fluid state has remained elusive. The other method involves using shock waves, but these create the necessary pressure for only microseconds, and the results are often difficult to interpret. We simply lack the technology to create and hold a stable sample of this material for detailed analysis. This means that everything we know or think we know about this central layer of Jupiter is based on theoretical models and indirect measurements from missions like Juno. The behavior of hydrogen under these extreme conditions is governed by quantum mechanics, making the calculations incredibly complex. Different models predict slightly different properties: how viscous it is, how it convects, and precisely where the transition from gas to metal occurs. Juno's measurements of Jupiter's gravitational and magnetic fields are providing crucial data to test these models, but many questions persist. Is the ocean well mixed, or are there layers within it? How does the suspected helium rain interact with this metallic sea? The answers to these questions are locked within the behavior of this enigmatic material. Jupiter's liquid metallic hydrogen ocean is more than just a curiosity. It is a fundamental state of matter that governs the inner workings of a giant planet, and until we can crack the code of its creation here on Earth, it will remain one of the most profound and tantalizing mysteries in our solar system. This striking absence of clear, stable stratification is our next great puzzle. On Earth, our atmosphere is neatly organized into distinct layers: the troposphere where weather happens, the stable stratosphere above it, then the mesosphere, and so on. Each layer has a specific temperature profile and composition, separated by boundaries where temperature inversion occurs. For a world as massive as Jupiter, with an atmosphere thousands of miles deep, scientists naturally expected to find a similar, albeit more complex, layered structure. Models predicted a sophisticated, layer cake arrangement deep beneath the cloud tops, with different cloud decks of ammonia, ammonium hydrosulfide, and water ice forming at specific pressures and temperatures, each separated by relatively stable layers of gas. But when the Juno spacecraft began probing the planet's interior with its microwave radiometer, it returned a picture that was anything but orderly. Instead of finding crisp, well-defined layers, Juno discovered that Jupiter's atmosphere is deeply and chaotically mixed, with materials churning vertically across vast distances in a way that completely defies our conventional understanding of atmospheric science. The data revealed that ammonia, for instance, is not confined to a neat, high-altitude cloud deck as once thought. Its abundance fluctuates wildly with depth, suggesting powerful plumes are constantly dredging it up from the deep interior, while dry downdrafts are pulling ammonia-poor air from the upper atmosphere far below. This creates a massive, planet-wide mixing that effectively blurs the lines between what should be separate atmospheric strata. The same appears to be true for water. Rather than a well-mixed reservoir, Juno found it is distributed in uneven, patchy concentrations, further evidence that the atmosphere is being turned upside down by colossal circulation patterns we are only beginning to map. This profound vertical mixing suggests that Jupiter's atmosphere operates more like a single, massive boiling pot than a layered cake, with heat from the interior driving convection on a scale that is almost unimaginable. So what is the engine behind this relentless churn? The answer seems to lie with the same internal heat source that powers the planet's weather: This tremendous energy radiating from the planet's core creates incredibly powerful convection currents. Columns of warm gas, rich with volatiles like ammonia and water, race upward from depths of hundreds of miles. When they reach the cold cloud tops, they cool and sink back down, only to be reheated and rise again. This constant, violent overturning acts like a planetary-sized blender, thoroughly mixing the atmosphere and preventing the formation of stable, long-lasting layers. The process is supercharged by Jupiter's rapid rotation, which organizes these upwellings and downwellings into the familiar banded structure we see, but it does not inhibit their vertical power. This discovery forces a major revision of our atmospheric models. It indicates that the processes governing circulation on gas giants are fundamentally different from those on terrestrial planets. Our own atmosphere is primarily heated from above by the Sun, which creates stable conditions conducive to layering. Jupiter, by contrast, is heated from within, and that heat flow is likely inconsistent, generating localized hotspots and massive convective cells that punch through any incipient stratification. The missing layers are not really missing. They are being continuously erased and reformed by a dynamic, turbulent interior that refuses to stay neatly organized. This chaotic mixing is a direct window into the extreme energy and fluid dynamics at work deep within the planet, revealing a world that is far more thermally alive and violently agitated than we ever previously conceived. But beyond the visible light and the churning depths lies a symphony of sound that we cannot hear, a raging torrent of radio waves that makes Jupiter the solar system's most powerful natural radio station after the Sun itself. These are not gentle signals, they are stupendous outbursts of energy that can, at their peak, outshine the Sun in radio wavelengths, and they represent one of the planet's most audible and rhythmic mysteries. If our ears could tune into these frequencies, the sounds from Jupiter would be a cacophony of eerie shrieks, hollow whistles, and deep, rhythmic booms, a soundtrack of pure energy generated by the complex dance between the planet, its magnetic field, and its volcanic moon. These radio emissions come in several distinct varieties, each with its own origin story and strange behavior. The most powerful and perplexing are the decametric radio waves, which are bursts of long wavelength radiation that pulse with an almost clockwork regularity. For decades, astronomers noticed that the intensity of these radio storms seemed to vary not just randomly, but in a pattern that was closely tied to the orbital position of the moon Io. It was a bizarre connection. How could a moon over 400,000 miles away dictate the rhythm of a planet's most powerful emissions? The answer lies in an extraordinary electrical circuit of cosmic proportions, with Io acting as a key component. Io is a world of relentless volcanic fury, spewing tons of sulfur dioxide and other gases into space every second. This constant outgassing creates a tenuous but significant atmosphere around the moon, and Jupiter's powerful magnetic field strips ions from this atmosphere, creating a vast, donut-shaped cloud of plasma that traces Io's entire orbit. This structure is known as the Io plasma torus. As Jupiter's magnetic field spins past the comparatively slow-moving Io at a speed of over 45 miles per second, it creates a million-amp electrical current that flows along the magnetic field lines, connecting Io directly to Jupiter's polar regions. This current, known as the Io flux tube, is the engine behind the radio roar. The process works like a colossal cosmic generator. The relative motion between Jupiter's magnetic field and the Io plasma torus generates a powerful electric field, which accelerates electrons to nearly the speed of light. These high-energy electrons then spiral along the planet's magnetic field lines, and as they are accelerated, they naturally emit radio waves through a process called cyclotron maser instability. It's a complex name for a relatively simple concept. When charged particles are whipped around a magnetic field at incredible speeds, they broadcast their energy. This is why the emissions are so tightly linked to Io's position. The strength of the current, and thus the power of the radio burst, depends on the precise angle between Jupiter, Io, and an observer. The radio waves beam out from the polar regions in a narrow, headlight-like pattern, meaning we on Earth only hear the full intensity of the storm when that beam sweeps across our location. But the mystery deepens beyond this elegant explanation. Not all of Jupiter's radio emissions are so predictable. The planet also emits lower-frequency decametric radiation that seems untethered to Io, suggesting other dynamic processes are at work within the magnetosphere. Furthermore, there are the mysterious millisecond-long bursts known as S-bursts and longer L-bursts that overlap, creating a complex radio tapestry that we are still learning to decode. The sheer power and regularity of these signals make Jupiter a natural laboratory for studying how celestial bodies generate radio waves, a process that likely occurs on exoplanets and brown dwarfs throughout the galaxy. This invisible, screaming beacon reminds us that Jupiter's influence is not just gravitational or visual. It is an electromagnetic titan, constantly broadcasting the powerful and intricate forces at work within its stormy heart. While the Great Red Spot commands attention with its centuries-old rage, a far more elusive and ghostly feature has been found haunting Jupiter's polar skies, a vast, transient dark patch that scientists have named the Great Cold Spot. This isn't a storm of clouds and wind, but a profound chill in the upper atmosphere, a region of unexpectedly cold air sprawling over 7,000 miles wide, larger than the entire Earth. Unlike its famous crimson cousin, this spot is invisible to optical telescopes. It was only discovered in 2017 by astronomers analyzing subtle temperature data from a telescope in Hawaii. Its existence reveals a completely new kind of weather phenomenon, one intricately tied not to the churning clouds below, but to the furious auroral fire raging above it, presenting a stunning connection between the planet's polar light shows and its upper atmospheric weather. The sheer scale and nature of this feature are baffling. It's not a fixed, permanent structure, but a highly variable one, constantly changing in shape and size, and at times even disappearing entirely before reforming. Temperature measurements show it is around 200 degrees Celsius colder than the surrounding thermosphere, which itself is typically heated to oven-like temperatures by the auroras. This creates a massive, shadow-like hole in the heat map of Jupiter's pole. The most compelling clue to its origin is its location, for it sits directly beneath the main auroral oval, the heart of Jupiter's most powerful energy deposition. This has led scientists to a fascinating and counterintuitive theory. The Great Cold Spot is likely not a lack of energy, but rather a direct and dramatic side effect of it. The prevailing explanation paints a picture of a vast atmospheric tug of war. Jupiter's relentless auroras act like a colossal heat gun, constantly blasting the polar upper atmosphere with energetic particles and pumping tremendous amounts of energy into it. This should make the region uniformly searing hot. The existence of a persistent cold spot right in the middle of this inferno suggests that some other powerful process is actively and rapidly sucking that heat away. Researchers believe the mechanism is driven by the planet's mighty magnetic field. The same energetic particles that create the auroras also ionize the gases in the upper atmosphere, turning them into a plasma. This plasma, caught in the grip of Jupiter's magnetic field, is then funneled away from the poles and toward the equator. In doing so, it effectively acts as a massive planetary cooling system, carrying thermal energy away from the auroral region and dumping it into the middle atmosphere. This creates a dynamic equilibrium, a constant battle between heating and cooling. The auroras pump energy in, and the outflow of plasma pulls it out. The Great Cold Spot is the visible, or rather thermal, signature of this cooling process winning out in that specific location. It's a delicate balance which explains the spot's transient nature. Fluctuations in the intensity of the auroras, which are themselves influenced by the solar wind and the volcanic output of Io, would directly affect the efficiency of this cooling. A surge in auroral activity might momentarily overwhelm the process, causing the spot to shrink or vanish, while a lull might allow the cooling to dominate, making the spot expand. This makes the Great Cold Spot not a static object, but a living, breathing manifestation of an ongoing energy transaction in Jupiter's atmosphere, a transaction happening on a scale we've never witnessed on any other world. The discovery forces us to reconsider the complexity of energy flow on gas giants. It reveals that these planets have their own unique and powerful methods of redistributing heat, methods that operate through the complex interplay of magnetism and plasma physics rather than simple convection. This has profound implications for our understanding of exoplanets, many of which are hot Jupiters orbiting close to their stars and subject to even more extreme stellar winds and radiation. The Great Cold Spot is a ghostly footprint, a temporary void that speaks volumes about the invisible forces shaping the environment of our solar system's largest planet, proving that even in the greatest heat, a profound cold can find a way to persist. While the polar cyclones and the Great Cold Spot reveal the complex weather at the extremes of Jupiter's sphere, the planet's entire atmosphere is defined by a fundamental and puzzling feature: its jet streams. From a distance, those elegant bands of cream and ochre appear serene, but in reality, each band is a raging river of wind, a jet stream moving at speeds that dwarf anything on Earth. The fastest of these, particularly those near the equator, can scream along at over 400 miles per hour, yet this isn't a uniform planetary gale. The wind speeds are wildly inconsistent, varying dramatically not just by latitude but, as we've more recently discovered, by depth as well. This presents a major conundrum. Jupiter rotates as a solid body, completing a full turn every 9 hours and 56 minutes. This rapid spin should, in theory, create a powerful force that organizes the atmosphere into a relatively uniform system. So why do we see such a chaotic and varied map of wind velocities? What unseen brakes and accelerators are at work deep within the cloud layers? The mystery deepens when we consider the vertical structure. For a long time, we could only measure the wind speeds at the very cloud tops, the visible surface of this vast atmospheric ocean. But the Juno mission, with its ability to peer beneath the clouds using microwave technology, revealed something astonishing. These powerful jet streams, it turns out, are not merely surface phenomena. They extend thousands of miles down into the planet's interior. However, they don't all extend to the same depth. Some of the prevalent east-west jets appear to be shallow, perhaps only 200 miles deep, while others, particularly the major prograde jets, seem to plunge thousands of miles downward, reaching as far as our instruments can see. This suggests that the engine driving these winds isn't the sun, as it is on Earth, but something much deeper and more powerful. The varying depths of these wind systems imply that they are anchored to different sources of energy and momentum within the planet's interior, like roots tapping into separate aquifers. One leading theory to explain this inconsistent power involves the planet's tremendous internal heat flow. The idea is that the heat rising from Jupiter's core doesn't do so evenly. It likely ascends in massive, concentrated columns or plumes. Where these thermal plumes rise, they could power stronger, deeper jet streams. In regions between these plumes, where the upwelling is less intense, the winds might be weaker and more shallow. This would create a planetary pattern of atmospheric circulation that is fundamentally three-dimensional, with deep-rooted weather systems interacting in a complex dance that we are only beginning to map. Another fascinating hypothesis involves the role of magnetic fields. At great depths where hydrogen transitions into its metallic, electrically conductive form, the powerful magnetic field generated within could interact with the atmospheric winds. This magnetic drag could act as a braking mechanism on some of the deeper jet streams, slowing them down relative to their surface expressions and explaining the velocity differences we observe at various levels. The rapid rotation of Jupiter itself adds another layer of complexity through the Coriolis effect. This force, which deflects moving air to the right in the northern hemisphere and to the left in the south, is immensely stronger on Jupiter than on Earth due to the planet's swift spin. This powerful deflection is what organizes the chaotic convection into the neat parallel bands we see. However, it doesn't dictate their speed. The Coriolis effect acts as an organizer, not an engine. The engine itself is the internal heat, and the inconsistent output of that engine, filtered through the planet's complex interior structure and its own magnetic field, creates the patchwork of wind speeds we observe. This tells us that Jupiter's beautiful striped exterior is not just a painted-on surface feature. It is the visible expression of a deep, turbulent, and multifaceted interior engine, a system where dynamics occurring thousands of miles beneath the clouds directly dictate the ferocity of the winds that scream across its surface. But perhaps the most bewildering aspect of Jupiter's electrical storms is their fundamental difference from our own. The distribution of this lightning is completely inverted from the pattern we see on Earth. On our planet, thunderstorms are a tropical affair, clustering near the warm, moist equator where solar heating is most intense. Jupiter, by contrast, has almost no lightning near its equator. Instead, its electrical fury is overwhelmingly concentrated at the poles, a bizarre reversal that left scientists utterly perplexed for decades. The early data from the Voyager missions hinted at this, but it was Juno that confirmed the pattern with absolute certainty, detecting thousands of radio signatures from lightning discharges that were almost exclusively clustered in the high latitudes. This finding upended the classic model for how lightning forms because it points to a completely different energy source and a completely different atmospheric recipe. On Earth, our thunderstorms are powered from above by the sun. Solar energy heats the surface, causing warm, moist air to rise and form the towering cumulonimbus clouds where charge separation occurs. Jupiter is too far from the sun for this to be the primary driver, especially at its poles, which receive even less sunlight. The engine for its storms must be internal. The answer lies in the planet's own intense heat rising from its deep interior. This internal furnace drives convection globally, but something special must be happening at the poles to channel that energy into such prolific electrical activity. One compelling theory focuses on the stability of the atmosphere. Jupiter's equator is dominated by incredibly powerful, stable jet streams that might actually suppress the large-scale vertical convection needed to build massive storm clouds. The polar regions, however, are more dynamically quiet in terms of zonal winds, potentially allowing thermal plumes from the deep interior to rise much more freely and powerfully, creating the ideal conditions for towering thunderheads to form. The very nature of the lightning itself might also be alien. While terrestrial lightning is generated by the separation of charges within water-based clouds, there is strong evidence that Jupiter's bolts may be forged in a strange slurry of water and ammonia. At the frigid temperatures found in Jupiter's upper atmosphere, pure water clouds would be frozen solid, making charge separation difficult. However, ammonia acts as an antifreeze. When mixed with water, it creates a liquid ammonia-water solution that can exist at much colder temperatures. This exotic mixture could exist in a slushy state in the cloud layers, allowing for the same sort of droplet collision and charge separation that drives lightning on Earth, but under utterly alien chemical conditions. Some scientists even speculate that these ammonia-water hailstones, known as mushballs, could be a key part of the process, falling through the atmosphere and creating electrical imbalances as they go. This means we might not just be seeing lightning on another planet. We might be witnessing an entirely new type of atmospheric electrochemistry at work, one that operates by rules we are still struggling to comprehend. This brings us to a chemical detective story hidden within the swirling clouds, a mystery centered on one of Jupiter's most common yet curiously elusive compounds, ammonia. We know from our studies of the solar nebula that Jupiter should be rich in nitrogen, and much of that nitrogen should be bound up in ammonia gas, a simple molecule of 1 nitrogen and 3 hydrogen atoms. Early models of the planet's atmosphere predicted a relatively uniform and abundant distribution of this gas, forming a bright, white deck of ammonia ice clouds at a specific cold altitude. But when scientists began probing the atmosphere with advanced instruments, they found something deeply puzzling. The ammonia was not where it was supposed to be. In some regions, particularly near the equator, it appeared severely depleted, almost as if something was actively scrubbing it from the air. In other areas, especially within the powerful polar cyclones, it was found in surprising abundance. This uneven distribution defies the basic principles of atmospheric convection, which should, over time, mix the atmosphere into a relatively homogeneous state, and it sent researchers on a hunt for the missing ammonia. The first major clue came from the Galileo probe's descent in 1995, as it plunged into a peculiarly dry and cloud-free area near the equator. Its mass spectrometer recorded ammonia levels that were far lower than expected. For over 20 years, this single data point stood as an anomaly without a clear explanation. Was this specific spot just a strange fluke, or was it a window into a larger planetary-scale process? The arrival of the Juno spacecraft finally provided a global perspective, and its microwave radiometer confirmed that the ammonia was indeed distributed in a bizarre, patchy manner. It wasn't uniformly mixed, it was concentrated in large plumes and depleted in vast areas, creating a planetary-scale mosaic of chemical richness and poverty. This wasn't a simple case of clouds obscuring our view. The gas itself was fundamentally uneven. The question became, what powerful mechanism could be so efficient at removing ammonia from some parts of the atmosphere while concentrating it in others, and doing so against the planet's relentless mixing forces? Planetary scientists have developed several compelling, and at times dramatic, theories to explain this chemical mystery. One of the most fascinating hypotheses involves a form of precipitation far more exotic than anything we experience on Earth: ammonia snowfall. The process begins deep within the atmosphere, where temperatures and pressures are much higher. Here, water likely exists as a liquid, forming vast hidden water clouds. Theory suggests that when powerful convective plumes carry ammonia and hydrogen sulfide gas upward from the deep interior, they encounter this water layer. In the tumultuous conditions, these gases can combine with water to form a new substance, ammonium hydrosulfide, a kind of salty sludge. As this mixture is carried even higher into the colder upper atmosphere, it can crystallize into ammonia water ice particles. These mushballs, as scientists have called them, are essentially hailstones made of a slushy ammonia-water mixture. Because they are much heavier than the surrounding gas, they fall like stones, pulling the ammonia deep down into the atmosphere where our instruments can no longer easily detect it. This process would effectively create localized, violent storms that act as ammonia scavengers, raining the compound out of the upper atmosphere and explaining the mysterious depletions. But the mushball theory isn't the only player in this game. Other processes could be working in concert or in different regions. Another possibility involves complex chemical reactions. Jupiter's atmosphere is bombarded by ultraviolet light from the sun and is filled with energetic particles from its own radiation belts. This constant energy input could be breaking apart ammonia molecules high in the atmosphere, allowing the nitrogen to participate in other chemical reactions that form more complex compounds, perhaps even the mysterious chromophores that give the clouds their beautiful reddish and brownish hues. In this scenario, the ammonia isn't falling. It's being chemically transformed into something else, effectively hiding it from our detectors that are tuned to find the simple ammonia molecule itself. Furthermore, the planet's complex circulation patterns likely play a crucial role. The same powerful downdrafts that create the dark, dry belts might be dragging ammonia poor air from the upper atmosphere deep into the interior, while the upwelling zones could be transporting ammonia-rich air upward, creating those temporary pockets of abundance that Juno observed. The missing ammonia is more than just a chemical accounting error. It's a direct probe into the hidden dynamics of Jupiter's deep atmosphere. This uneven distribution tells us that the processes at work are far more vigorous and efficient than we ever imagined. They reveal a world where entire oceans of water may slosh unseen beneath the clouds, where exotic forms of hail fall from skies of hydrogen, and where chemistry and weather combine on a scale that permanently alters the composition of the air. Solving this mystery isn't just about finding where the ammonia went. It's about mapping the hidden circulatory system of a giant, a system that governs everything from the colors of its clouds to the very energy that drives its endless storms. Just when we thought we had a handle on Jupiter's internal structure from its lopsided magnetic field and fuzzy core, the Juno mission delivered yet another bombshell that has forced us to rethink the very fundamentals of planetary physics. This time, the surprise came from meticulously mapping the planet's gravity field. For any world that rotates as rapidly and uniformly as Jupiter does, we expect its gravity field to be almost perfectly symmetrical. The immense centrifugal force generated by its spin should fling mass outward at the equator, creating a slight bulge, but the distribution of that mass should be smooth and consistent from the north to the south. It should be a textbook oblate spheroid, but Jupiter, as it so often does, defies the textbook. Juno's incredibly precise measurements of the planet's gravitational tug revealed a startling and significant asymmetry between the northern and southern hemispheres. The gravitational pull is noticeably stronger in the north than it is in the south. This was not a minor anomaly, it was a fundamental feature indicating that mass is not distributed evenly deep within the planet. This lopsided gravity field is a direct signal from the hidden depths, a cryptic message about flows and structures we cannot see. This discovery is so revolutionary because gravity is the most direct probe we have into a planet's interior mass distribution. By tracking the tiny wobbles in a spacecraft's orbit, scientists can create a detailed map of where mass is concentrated inside the planet. A symmetrical gravity field points to a well-ordered, layered interior. An asymmetrical one is a glaring sign that something is off balance, that the deep engine of the planet is churning in a way that creates permanent imbalances. This north-south discrepancy suggests that the immense weather systems and jet streams we see on the surface are not just skin-deep phenomena. They must be deeply rooted, extending thousands of miles down into the planet's interior. The powerful atmospheric flows, those raging rivers of gas that form the belts and zones, are apparently so massive and organized that they themselves have a measurable gravitational signature. It means the atmosphere isn't just a thin, restless veneer on top of a calm interior. It is an integral part of a much deeper circulatory system, but the story is likely even more complex than just deep winds. While these flows contribute to the asymmetry, many scientists believe they cannot account for all of it. This has led to the compelling idea that the imbalance might also be frozen into the planet's very structure, a relic of its violent past. One fascinating theory suggests that the asymmetry could be a scar from a colossal impact in the early solar system. If a massive planetary embryo, perhaps 10 times the mass of Earth, struck a young Jupiter off-center, it could have splattered material unevenly through the interior, creating a permanent mass imbalance that has persisted for over 4 billion years. Alternatively, the process could be ongoing and dynamic, related to the way the exotic materials inside Jupiter behave. The helium rain we discussed earlier might not be falling uniformly. If it is precipitating more heavily in one hemisphere than the other, it could be creating a regional density difference that subtly alters the gravity field. Or it could be that the fuzzy, diluted core itself is not symmetrical, with its dissolved rocky material spread unevenly, creating a heavier region in the planet's north. This gravitational puzzle forces a complete rewrite of how we model gas giants. Our models assumed a high degree of symmetry for simplicity's sake, but Jupiter is showing us that giant planets are messy, complex, and fundamentally lumpy. This has profound implications for how we interpret data from exoplanets. When we estimate the composition and structure of distant hot Jupiters based on their mass and radius, we are likely making assumptions about symmetry that may be completely wrong. A planet's true character might be hidden in its gravitational asymmetries, a detail we cannot yet detect from light years away. Jupiter's lopsided gravity is a powerful reminder that to truly know a world, we must understand not just its outward appearance, but the deep, hidden currents and ancient scars that shape its very being. And now we arrive at a mystery that is fundamental to almost everything we've discussed so far, a single, staggering fact that underpins the planet's most spectacular features, its rotation. Jupiter, a colossus with a diameter 11 times that of Earth and a mass greater than all other planets combined, performs a complete pirouette in less than 10 hours. This makes it the fastest spinning planet in our solar system by a significant margin, a title it holds not by a small margin but by a breathtaking one. This rapid spin is the invisible engine behind Jupiter's flattened shape, its raging jet streams, its chaotic magnetic field, and its auroral fireworks. But this fact itself presents a profound puzzle. In the vacuum of space, there is no friction to slow a planet's spin, so theoretically, once it's spinning, it should just keep spinning. The real mystery isn't why it's still spinning fast, but how it achieved such an incredible rotational velocity in the first place, and what internal forces might be subtly influencing that spin today. The most immediate and visible consequence of this whirlwind rotation is Jupiter's distinct shape. A planet's rotation creates a centrifugal force that flings material outward from its equator. For a slow rotator like Earth, this effect is minimal, resulting in a nearly perfect sphere with only a slight equatorial bulge. But for Jupiter, the force is so tremendous that the planet is visibly squashed. Its equatorial diameter is over 5,000 miles wider than its polar diameter, giving it the appearance of a slightly flattened beach ball. This oblate spheroid shape is a permanent testament to the power of its spin, a direct physical manifestation of the kinetic energy stored in its rotation. This isn't just a surface effect. This flattening dictates the flow of its atmosphere, helping to organize those chaotic cloud bands into the relatively neat parallel stripes we observe from afar. So how did this behemoth get spinning so ferociously? The answer is likely locked in the planet's violent birth. The leading theory of gas giant formation, core accretion, suggests Jupiter began as a solid core of rock and ice. As this embryonic core grew, its gravity began to pull in vast amounts of hydrogen and helium gas from the surrounding solar nebula. The key to the spin mystery lies in the physics of this collapsing cloud of gas. As the nebula collapsed inward under gravity, a principle known as the conservation of angular momentum took over. Much like a figure skater pulling their arms in to spin faster, the contracting cloud of gas naturally began to rotate more and more rapidly as it shrunk in size. The initial tiny bit of spin inherent in the primordial solar nebula was amplified exponentially during this collapse, imprinting the young Jupiter with its incredibly fast rotation rate right from the very beginning. It was in essence born spinning. However, the story doesn't end there. While there's no air resistance in space to slow it down, there might be other, more subtle forces at work deep within the planet that could be acting as a very slight brake or, conversely, an accelerator. One intriguing possibility involves the planet's magnetic field. Jupiter's magnetic field is generated within its deep ocean of liquid metallic hydrogen, a region that is itself spinning at a phenomenal rate. But this dynamo region is coupled to the overlying atmosphere through magnetism. The powerful magnetic field, which is rooted in the interior, extends out through the entire atmosphere and into the magnetosphere. If there is any difference in rotation rate between the deep interior and the outer atmosphere, a phenomenon called differential rotation, the magnetic field could create a tension that acts to transfer angular momentum, potentially slowing one part down while speeding another up. It's a complex internal tug-of-war that could be causing minute changes in the planet's overall spin over millions of years. Another fascinating factor could be Jupiter's immense moon system. The gravity of its large Galilean moons, Io, Europa, Ganymede, and Callisto, exerts a constant tidal pull on the planet. While this effect is far more dramatic on the moons themselves, it also has a tiny, cumulative impact on Jupiter. This tidal interaction can very gradually transfer rotational energy from the planet to the orbits of the moons, a process that acts as an incredibly weak braking mechanism. Over billions of years, this could have slowed Jupiter's spin by a small but measurable amount. Conversely, some models suggest that atmospheric processes, like the massive weather systems and the tremendous heat rising from the interior, could actually inject energy and influence the rotation in different ways. The precise interplay of these forces, the primordial spin, the magnetic coupling, and the tidal interactions, creates a dynamic system where the rotation, while stable on human timescales, is part of a long, slow cosmic dance that continues to shape the planet's deepest dynamics. This incredible spin is not just a static fact. It is the vibrant, driving heartbeat of Jupiter, powering its storms, shaping its form, and generating the titanic forces that make it the magnificent and mysterious king of planets. While the Great Red Spot is Jupiter's most famous storm, it is far from the only long-lived feature carving its way through the planet's cloud tops. For much of the 20th century, astronomers tracking the giant planet documented a trio of massive, brilliant white ovals slowly drifting in the southern hemisphere. These were not fleeting tempests, they were stable, anti-cyclonic storms rotating counter to the surrounding flow. That persisted for over 60 years, from their first clear observations in the 1930s until a stunning and unexpected merger at the turn of the millennium. Their longevity and serene white appearance, so different from the angry red hue of their more famous cousin, presented a compelling mystery. Why did some giant storms on Jupiter turn a deep, ominous red while others remained a brilliant, reflective white? And what internal dynamics allowed these vast white ovals to maintain their separate identities for decades, only to eventually converge and combine in a spectacle of atmospheric violence? The key to understanding the white ovals lies in their place within Jupiter's complex atmospheric orchestra. They are high-pressure systems similar to the Great Red Spot, where air is slowly descending. This sinking motion prevents darker, colorful compounds from welling up from the deeper atmosphere, leaving the upper cloud decks dominated by bright, fresh ammonia ice crystals that brilliantly reflect sunlight. This is what gives them their pearly white appearance. They are, in essence, colossal zones of atmospheric clarity and cold. Their stability is granted by the same powerful Coriolis effect that organizes the jet streams, effectively trapping them between the raging rivers of wind and preventing them from drifting apart or dissipating easily. For decades, they behaved like three solitary, slow-dancing giants, maintaining a cautious and predictable distance from one another. The mystery of their longevity deepened in the late 1990s when two of these ancient ovals began to drift closer together. In 1998, in an event that captivated planetary scientists, these two behemoths did something no one had ever witnessed before on such a scale. They merged. Over a period of months, the two storms spiraled around each other in an increasingly tight dance before finally coalescing into a single, larger oval. But the atmospheric drama wasn't over. This new, larger storm then proceeded to engage with the third and final white oval, and by the year 2000, they too had merged. In a span of just 2 years, three storms that had existed separately for over half a century had become one. This newly consolidated storm, now large enough to be visible in amateur telescopes, underwent a remarkable transformation. It began to change color, gradually darkening from a brilliant white to a reddish-brown hue, eventually earning itself the unofficial title of Red Spot Junior or Oval BA. This spectacular sequence of events provided a treasure trove of data and raised profound new questions. The merger itself demonstrated that even the most stable-looking features on Jupiter are part of a dynamic and evolving system, where conservation of energy can lead to sudden and dramatic reorganization. The subsequent color change was perhaps the most tantalizing clue. Why would a storm turn red only after it achieved a certain size? The leading theory suggests that the merger created a storm powerful enough to alter its own internal dynamics. As the larger, combined oval intensified, it may have begun to draw up material from far deeper in the atmosphere than it could before. From these great depths, it could have pulled complex chemical compounds known as chromophores, likely complex polymers of sulfur, phosphorus, or hydrocarbons that had been colored by the intense heat and pressure of the interior. When these compounds are exposed to ultraviolet light from the sun at the higher cloud tops, they darken, creating the signature reddish hues we see. A smaller storm simply lacks the power and vertical reach to act as this kind of atmospheric elevator, forever doomed to remain white. The story of the white ovals provides a fascinating counterpoint to the Great Red Spot. It suggests that a storm's color is not a fixed identity but a function of its size, power, and depth. It reveals that Jupiter's atmosphere is a system of constant negotiation and occasional consolidation, where even features that appear permanent for a human lifetime are merely players in a much longer, grander cycle of energy and motion. The fact that we witnessed this merger within our own observational timeline was a stroke of incredible luck, a front-row seat to a planetary process that might happen only a few times a century. It offers a humbling reminder that to truly understand the climate of a giant planet, we must think in time frames that dwarf our own, watching patiently for the slow, majestic dance of its largest storms to reveal its deepest secrets. Yet for all the dynamic churn of its weather and the profound depth of its winds, one of the most telling clues about Jupiter's origin lies not in its motion, but in its chemistry specifically, the surprising and uneven distribution of heavy elements throughout its atmosphere. According to long-standing planetary formation theories, a gas giant like Jupiter should be a paragon of chemical uniformity. The immense heat and turbulence generated during its formation, combined with billions of years of powerful convective mixing from its hot interior, should have thoroughly homogenized its atmosphere. The heavy elements, things like carbon, nitrogen, sulfur, and argon, that were pulled in during its accretion should be evenly mixed from the cloud tops down to the deepest interior. This is a foundational principle of how we thought these planets worked, but Jupiter, as it so often does, has taken that textbook assumption and torn it to shreds. Data from the Juno mission has revealed that these heavy elements are not uniformly distributed at all. Instead, they are scattered in a bizarre, clumpy, and uneven manner, creating a planetary-scale mosaic of chemical richness and poverty that forces us to completely rethink how this giant was built. This discovery is monumental because these elements are tracers, cosmic fingerprints that tell the story of how and where the planet formed. The prevailing core accretion model suggests Jupiter first gathered a solid core of ice and rock from the cold outer solar system. Once this core became massive enough, its gravity began vacuuming up enormous amounts of the primordial solar nebula, mostly hydrogen and helium gas. According to this theory, the planetesimals that delivered the heavy elements should have been thoroughly vaporized and mixed into this growing gaseous envelope, creating a well-stirred chemical soup. Juno's measurements of Jupiter's gravitational field initially supported this by revealing a fuzzy, diluted core, suggesting that the original rocky material had indeed mixed inward. But the atmospheric measurements tell a different and conflicting story. If the interior were well mixed, the atmosphere should be too. The fact that it is not suggests that the story of Jupiter's assembly was far more violent, piecemeal, and incomplete than we ever imagined. So what could cause such profound and persistent chemical unevenness? Scientists are investigating several compelling and dramatic scenarios. One leading hypothesis suggests that Jupiter's formation was not a smooth, continuous process but a series of catastrophic impacts. Instead of gently accreting countless small planetesimals, a young Jupiter may have grown primarily by cannibalizing a few massive planetary embryos, each one a world in its own right, perhaps the size of Mars or even larger. These gargantuan impacts would have delivered enormous, concentrated slugs of heavy elements in single, violent events. If these impacts struck at different angles and depths, they could have deposited their elemental cargo in different layers of the atmosphere and interior without being fully mixed, creating permanent, localized reservoirs of richness. It's the difference between stirring a pinch of salt into a pot of soup versus dropping in a whole, undissolved Boolean cube. The flavor is there, but it's not evenly distributed. Another fascinating theory looks to the planet's interior dynamics for an answer. It's possible that certain regions inside Jupiter are effectively stagnant, with convection currents bypassing them entirely. In these quiet zones, heavy elements could have settled out and remained trapped, isolated from the churning currents that mix the rest of the planet. Alternatively, the very process of helium rain falling toward the core could be dragging other heavy elements down with it, effectively sequestering them in the deep interior and depleting them from the upper layers we can observe. This would create a permanent chemical gradient, with the upper atmosphere being more pristine and sun-like in its composition, while the deeper layers become enriched with a sinking rain of heavy elements. Furthermore, the immense pressure and temperature at certain depths might cause some elements to form stable compounds or even dissolve into the liquid metallic hydrogen in ways we don't yet understand, effectively hiding them from our remote sensors. This chemical puzzle is far more than an academic accounting error. It is a direct challenge to our understanding of planetary formation across the galaxy. Thousands of the exoplanets we've discovered are gas giants, many of them so-called hot Jupiters, orbiting perilously close to their stars. Our models for how these worlds evolved and migrated rely on assumptions about their internal composition and structure. If our own Jupiter, right here in our solar system, defies the basic principle of being well mixed, then we must seriously reconsider the formation history of every giant planet we've ever detected. The uneven distribution of elements is a cryptic message from Jupiter's deepest past, a record written in atoms of how chaos and violence built a king, and it suggests that the serene giant we see today is still holding onto the scattered, piecemeal evidence of its tumultuous birth. For centuries, the Great Red Spot has been the unwavering, furious eye of Jupiter, a constant presence observed by every telescope since the 17th century. It has endured as the solar system's most famous storm, a seemingly permanent monument to the planet's untamed power. But in recent decades, this colossal vortex has begun to behave in ways that have both fascinated and alarmed planetary scientists. High-resolution monitoring from spacecraft like Hubble and Juno has revealed a startling trend. The Great Red Spot is not just changing, it is actively shrinking. Its diameter has been decreasing at a rate of about 900 miles per year, a slow but relentless contraction that has seen it shed nearly a third of its size since detailed measurements began in the late 19th century. This isn't a sudden collapse, but a gradual diminishment that raises a profound and unsettling question. Are we witnessing the final, drawn-out death throes of this legendary storm, or is this merely another phase in its incredibly long and dynamic life? The changes go far beyond its physical size. The storm's very appearance is transforming. Its once vivid brick-red hue has been fading to a paler, salmon-orange color in recent years, and its classic oval shape has become more circular, almost as if it's being compressed from all sides. Even its internal dynamics seem to be shifting, with the winds in its outer ring accelerating even as the overall storm shrinks. These are not the signs of a stable, eternal system. They are the symptoms of a giant in flux, and unraveling the cause has become a priority for understanding not just this one storm, but the fundamental life cycle of weather patterns on gas giants. The central mystery is one of energy balance. What force, after at least 400 years of stability, is now causing this behemoth to wane? Planetary scientists are investigating several compelling theories, each pointing to a different aspect of Jupiter's complex atmospheric machinery. One leading idea focuses on the interaction between the spot and the smaller vortices that constantly swirl through the surrounding jet streams. For years, it was believed the storm sustained itself by cannibalizing these smaller storms, absorbing their energy and momentum to fuel its own fury. But recent observations suggest a more complicated relationship. It's possible that a change in the number, size, or behavior of these smaller eddies is now disrupting the spot's flow instead of feeding it. They might be acting like atmospheric parasites, chipping away at its edges and stealing its energy, gradually eroding its structure from the outside in. Another hypothesis looks inward to the deep energy sources that power all of Jupiter's weather. The Great Red Spot is ultimately a heat engine, drawing its power from the warm gases rising from the planet's interior. If there were a shift in these deep thermal currents, a change in the intensity or location of these upwellings beneath the storm, it could be starving the spot of its essential fuel. The storm might be shrinking simply because it's running on a leaner mixture, no longer able to maintain its grand scale. This theory connects the fate of the surface storm to the hidden, churning dynamics thousands of miles below, suggesting that the spot's health is a direct barometer for processes we cannot yet see. Perhaps the most intriguing possibility is that the spot's changes are part of a natural, cyclical process that operates on a century-long scale. Historical records suggest the storm was once far larger, perhaps big enough to swallow 3 Earths side by side in the late 19th century. Its current shrinkage could be part of a long-term oscillation where it contracts, possibly even disappears for a time, only to later reform from a new conjunction of smaller storms. The recent color change supports this idea of a natural cycle. The prevailing theory for its red color is that the storm acts like an elevator, dredging up chemical compounds from deep within the atmosphere. As the storm weakens and shrinks, its ability to lift these chemicals may be diminishing, causing the signature hue to fade. Its paling color could be a direct sign of its fading power. The question of its ultimate fate remains one of the great unsolved puzzles in planetary science. Will it continue to shrink until it vanishes entirely, leaving future astronomers to wonder at the empty space where a giant once raged? Or will it eventually stabilize at a new, smaller equilibrium, becoming a permanent but less dominant feature of the Jovian landscape? Its resilience has already defied all predictions for centuries, proving itself far more robust than any storm on Earth. Its gradual fading is not a sign of immediate demise, but a powerful reminder that even the most iconic features in our solar system are not frozen in time. They are dynamic, evolving entities, and the slow transformation of the Great Red Spot offers us a front-row seat to a planetary metamorphosis that unfolds over generations, challenging our perceptions of permanence in the cosmos. Moving from the colossal scale of its storms and the chemical puzzle of its atmosphere, we encounter a mystery that requires us to listen to Jupiter in an entirely different part of the spectrum, one that reveals an unexpected and baffling heat emanating from within. When scientists first turned microwave radio telescopes toward the giant planet, they expected to see a relatively smooth and predictable gradient of warmth. The theory was straightforward. They were measuring the thermal radiation from deep within the atmosphere, and since temperature generally increases with depth inside a gas giant, the microwave emissions should have painted a simple picture, appearing slightly brighter near the equator where we look through more of the warm, deep atmosphere and darker toward the poles. But Jupiter, as it so often does, refused to follow the predicted script. Instead of this smooth gradient, the maps showed a bizarre, mottled, and deeply uneven landscape of microwave light. Vast regions, particularly around the equator, were inexplicably bright and hot, while other areas were far darker and cooler than any model had anticipated. It was as if a cosmic painter had taken a brush and splattered random, brilliant hotspots across the planet's face, creating a pattern that defied all logical explanation for decades. This strange microwave glow isn't just a surface feature. It's a direct window into the atmospheric layers tens to hundreds of miles below the visible cloud tops. The microwaves are emitted by the warm gases themselves, primarily from the regions where ammonia and water vapor are abundant. The fact that this emission is so patchy and inconsistent means that the distribution of these gases and the temperatures at those depths is far more complex and chaotic than anyone had imagined. For a long time, the only data was from distant Earth-based telescopes, which provided a fuzzy and frustratingly low-resolution view of the phenomenon. The true nature of this microwave mystery remained locked away, a persistent anomaly without a clear cause, until the Juno spacecraft arrived with its revolutionary microwave radiometer, an instrument specifically designed to peer deep into Jupiter's belly and map this strange radiation in exquisite detail. What Juno found was even more bewildering than the original mystery. The microwaves revealed that the equatorial region is not just uniformly bright. It contains a bizarre and massive band of exceptionally high microwave emission that encircles the entire planet. This equatorial band is far hotter and more intense than the surrounding areas, indicating a shocking abundance of ammonia gas churning up from the deep interior. This directly contradicts the earlier data from the Galileo probe, which found a desert of ammonia at the equator. Juno solved that contradiction by revealing that the dryness was a local phenomenon. Globally, the equator is actually a superhighway for ammonia-rich air. But the puzzle only deepens from there. The microwave data also shows that this band is not static. It fluctuates and changes over time, with its brightness and boundaries shifting in ways that suggest powerful, unseen forces are constantly reshaping the deep atmosphere. Furthermore, the North Pole exhibits its own strange microwave signature, appearing much cooler and drier than the South Pole, adding a whole new layer of hemispheric asymmetry to the mystery. So what powerful engine is creating this bizarre, patchy microwave map? The leading theory points directly to the planet's tremendous internal heat flow and the colossal weather systems it generates. Jupiter's atmosphere is not a calm, stratified place. It is a single, seething ocean of gas where heat from the interior forces powerful plumes of warm, moist, ammonia-rich air to race upward from incredible depths. The bright microwave hotspots are likely the signatures of these massive upwellings, where columns of warm gas are punching through the colder upper atmosphere and releasing their pent-up thermal energy. Conversely, the dark, cool microwave regions probably mark areas where cooler, drier air is descending back into the depths in a planet-wide circulatory system. This creates a dynamic and uneven distribution of heat and chemicals, explaining the mottled microwave pattern. It's a sign of an atmosphere that is being violently overturned from within. However, the story may be even more complex. Some scientists speculate that the unusual properties of water itself deep within Jupiter could be contributing to the anomaly. At the immense pressures found thousands of miles down, water undergoes strange phase changes and can hold vast amounts of dissolved ammonia. The dynamics of this deep, hidden water reservoir, how it evaporates, condenses, and circulates, could be directly influencing the microwave emissions we detect far above. The peculiar microwave glow might be the faint, distant echo of a hidden water cycle operating on a scale and under conditions we can barely comprehend. a cycle where exotic forms of rain and evaporation shuffle heat and chemicals in ways that leave their unique fingerprint in the microwave spectrum. This unresolved anomaly reminds us that for every layer of Jupiter we peel back, another, deeper mystery is waiting beneath, challenging our models and inviting us to look even closer. This striking gap in the Jovian moon system presents a curious and counterintuitive puzzle. When we look at the architecture of other planetary systems, like Saturn's magnificent collection of moons, we see a much more continuous size distribution, with several significant mid-sized bodies like Enceladus and Mimas. Jupiter's family, by contrast, seems to have skipped a whole size class. Orbiting the planet are the 4 massive Galilean moons, each a world in its own right, and then a collection of over 80 much smaller, irregularly shaped moons, most less than 250 kilometers in diameter. There is nothing in between. This isn't a case of us simply not having found them yet. Our surveys are thorough enough that we would have detected any substantial intermediate objects. Their absence is a real and telling feature of the system, a clue written in negative space that points to a violent and exclusive history of formation around the solar system's largest planet. One of the most compelling explanations for this missing middle class of moons is a process known as the push of the gas. This theory takes us back to the very beginning, when Jupiter itself was still a young protoplanet, surrounded by its own swirling disk of gas and dust, a miniature version of the solar nebula from which it was born. It was within this circumplanetary disk that Jupiter's moons are believed to have formed, coalescing from the material that spiraled inward. The 4 Galilean moons were likely the first and fastest to form, accreting material rapidly before the gas of the disk could dissipate. Their immense gravity would have begun to interact with this surrounding gas, creating a powerful dynamic friction. As any potential medium-sized moon embryos tried to form in the regions between these growing giants, their orbits would have been destabilized. The drag from the gas disk, combined with the gravitational pull of the large inner moons, would have acted like a cosmic broom, either pushing these smaller forming objects inward to be consumed by a hungry, growing Jupiter or hurling them outward to be lost to interplanetary space. This process would have effectively cleared the orbital neighborhoods around the large moons, preventing any other significant bodies from achieving stability and reaching a medium size. But the story doesn't end with the gas disk vanishing. Another powerful and relentless force has been sculpting the system for billions of years: orbital migration. The Galilean moons are locked in a beautiful and complex set of orbital resonances. For every one orbit that Ganymede completes, Europa completes exactly 2 and Io completes 4. This precise gravitational clockwork keeps their orbits stable but also causes tidal flexing, which heats the interiors of Io and Europa dramatically. However, these resonances also mean the moons are slowly moving outward from Jupiter over astronomical time. As they migrated, their gravitational influence would have swept through the system like a combined harvester, destabilizing the orbits of any smaller moons that might have been lingering in their path. Any moonlet that found itself in a resonant path with one of these migrating giants would have experienced periodic gravitational kicks, its orbit becoming more and more eccentric until it was eventually ejected from the system entirely or sent on a collision course with another body. This slow, grinding migration would have efficiently cleared out a vast swath of real estate around Jupiter, ensuring that no mid-sized moons could survive in the space between the giants and the distant, captured asteroids. This leads us to the final, most dramatic possibility, that the intermediate moons did indeed form, but they are simply no longer with us. The early solar system was a shooting gallery, a violent and chaotic place where colossal collisions were not just possible but commonplace. It is entirely plausible that a cohort of mid-sized moons once orbited Jupiter, only to be shattered in catastrophic impacts with each other or with rogue objects passing through the young system. The evidence for this may be all around us, Jupiter's faint and dusty ring system is likely composed of the pulverized remains of such collisions. Furthermore, many of the small, outer moons that we see today are probably not primordial. They are the surviving fragments of these ancient, shattered larger bodies. The missing mid-sized moons may not be missing at all, but rather they have been ground down into the fine dust and countless tiny moonlets that now populate the system, their original forms forever lost to a history of incredible violence. This gap in the lunar lineup is therefore not an empty space, but a monument to the dynamic and destructive forces that have shaped the Jovian system from its fiery birth to the present day. Yet as we turn our gaze from the planet itself to the invisible, hostile environment that surrounds it, we encounter a different kind of storm, one not of wind and cloud, but of pure, raw energy. Enveloping Jupiter is a donut-shaped region of space so fiercely radioactive, it represents the most hazardous environment in our entire solar system. These are the Jovian radiation belts, a zone where charged particles are trapped and accelerated to velocities approaching the speed of light, creating an invisible shroud of destruction that would instantly fry the electronics of any unshielded spacecraft. For decades, we assumed these belts, while intense, were relatively stable features, much like the milder Van Allen belts that surround Earth. But ongoing monitoring has revealed a shocking truth. Jupiter's radiation belts are wildly, unpredictably dynamic. Their intensity can spike or plummet by orders of magnitude in a matter of hours or days, and they contain electrons with energies so absurdly high they defy our best models of particle physics. The sheer force within these belts is a profound mystery, forcing us to ask what unimaginable particle accelerator is operating just beyond Jupiter's cloud tops. The scale of this radiation is almost incomprehensible. The electrons trapped here are not just energetic, they are ultra-relativistic, meaning they are moving at over 99.9% the speed of light. Their energy levels are measured in the tens of millions of electron volts, far beyond what any human-made collider can consistently produce, and according to our standard theories, far beyond what should be possible to sustain in a stable radiation belt. On paper, particles with this much energy should radiate away their power almost instantly or collide with other particles and be lost. Yet they persist in immense numbers, and their population doesn't just hold steady, it erupts. Observations from spacecraft and radio telescopes show that the entire belt system can experience colossal, planet-wide outbursts, during which the radiation levels increase 100-fold in a matter of hours, only to fade away just as suddenly. This isn't a gentle ebb and flow, it's the cosmic equivalent of a bomb repeatedly going off in slow motion, and we have little idea what is pressing the detonator. The central puzzle is the acceleration mechanism. How does Jupiter take ordinary charged particles and whip them into such an extreme frenzy? On Earth, radiation belt particles are primarily accelerated by waves propagating through the plasma of our magnetosphere. But Jupiter's requirements are on a completely different scale. Its accelerator must be vastly more powerful and efficient. One leading suspect is the planet's rapid rotation. Jupiter's magnetosphere is the largest physical structure in the solar system, and it spins like a rigid body with the planet's 10-hour day. This creates an incredible source of free energy, and scientists believe this spin may be driving powerful electromagnetic waves through the magnetospheric plasma. Particular attention has been paid to a type of wave called electromagnetic ion cyclotron waves, or EMIC waves. These waves could act like a surfer's perfect wave, but for electrons. As these waves travel through the radiation belts, electrons could ride them, gaining a tremendous energy boost with each wave they catch, eventually being accelerated to those insane, ultra-relativistic speeds. However, the rotation-powered wave theory might not be the whole story. Another compelling suspect is the violent and sudden process of magnetic reconnection. This occurs when the planet's powerful magnetic field lines, which are frozen into the plasma, become strained, break, and then reconnect in a different configuration. This reconnection process releases an enormous amount of stored magnetic energy almost instantaneously, like an elastic band snapping. This burst of energy can violently slingshot particles to incredible velocities. Jupiter's magnetosphere is a turbulent place, constantly buffeted by the solar wind and internally stressed by the centrifugal force of its own rotation and the plasma output from Io. It's likely a hotbed for magnetic reconnection events, which could be responsible for the sudden, dramatic outbursts that characterize the belts. It's possible that both mechanisms are at work, waves providing a steady, background acceleration, while reconnection events provide the periodic, violent injections of energy that push the system into overdrive. The greatest complicating factor in solving this mystery is the role of Jupiter's moons. The 4 large Galilean moons orbit within this hellish radiation environment, and their presence creates glaring, sharp-edged holes in the radiation belts. As the high-energy electrons encounter a moon like Ganymede or Europa, they are simply absorbed, creating a protective shadow in the moon's wake. But these moons, particularly the volcanic Io, are also sources of new particles. Io's constant eruptions feed the Io plasma torus, providing a fresh supply of particles for the acceleration mechanisms to work on. This creates a complex and dynamic feedback loop. The moons both deplete the radiation belts and replenish their fuel supply. Understanding this chaotic system is not just an academic exercise, it is absolutely critical for the future of exploration. The extreme and fluctuating radiation levels pose the single greatest danger to any future mission aiming to orbit Jupiter or land on Europa. Unlocking the secrets of this invisible maelstrom is the key to safely navigating the space around the solar system's king, allowing us to get close enough to unravel its other, equally profound mysteries. And so we arrive at our final and perhaps most profound mystery, one that shifts our gaze from the giant planet itself to one of its most captivating moons, and in doing so touches on our deepest question: are we alone in the universe? Lurking beneath the icy, cratered shell of Jupiter's moon Europa is strong evidence of a vast, global subsurface ocean containing more than twice the liquid water of all Earth's oceans combined. This makes Europa one of the most promising potential abodes for life beyond our planet. But this ocean world doesn't orbit in serene isolation. It is locked in a deadly gravitational embrace with Jupiter, and this relationship creates a baffling planetary protection puzzle. Jupiter's immense radiation belts, which we just explored, constantly bombard Europa's surface, creating a hostile environment that would sterilize any earthly life. Yet, this same brutal radiation might also be the very key that unlocks the possibility for life deep below, presenting a fascinating paradox that lies at the heart of modern astrobiology. The first layer of this puzzle is the sheer deadliness of the surface. Europa orbits squarely within the most intense region of Jupiter's radiation belts. Without a substantial atmosphere or a strong magnetic field of its own for protection, its icy surface is constantly pummeled by an onslaught of high-energy electrons and ions. This radiation shatters the water-ice molecules on the surface, creating a host of reactive chemicals called oxidants, such as hydrogen peroxide and sulfuric acid. For any potential life form on the surface, this would be a fatal environment, its cellular machinery torn apart by the relentless particle bombardment. This presents a major challenge for any future mission: how to land a spacecraft on Europa without its electronics being fried, and crucially, how to prevent any earthly microbes that might have hitched a ride from contaminating this pristine world before we can search for its own native life. This is the core of planetary protection, the discipline of safeguarding other worlds from our biology while we search for theirs. But the mystery deepens dramatically when we consider what might be happening beneath the ice. While the radiation makes the surface sterile, it might also be providing the very ingredients necessary for life in the ocean below. The theory is one of cosmic delivery. The constant radiation is creating those oxidants on the surface. Meanwhile, Europa's icy crust is geologically active with evidence of ice tectonics, plumes, and what scientists call chaos terrain, where blocks of ice might melt and refreeze. This churning could act as a conveyor belt, slowly dragging these surface oxidants down into the subsurface ocean over thousands or millions of years. Once there, they could mix with reductants, minerals and chemicals that well up from the moon's rocky seafloor, particularly around hydrothermal vents. On Earth, the meeting of oxidants and reductants provides a potent source of metabolic energy for entire ecosystems that thrive in total darkness. Jupiter's radiation, in this incredible scenario, could be indirectly powering a biosphere in Europa's hidden sea, providing the chemical energy for life in a world forever cut off from sunlight. This leaves us with a profound and unresolved tension. Is Jupiter's fierce radiation environment the ultimate barrier, a sterilizing fence that keeps life trapped and isolated in the abyss? Or is it the unexpected gardener, sowing the chemical seeds on the surface that then trickle down to feed life in the depths? The answer will dictate not only how we search for life, but also how we interpret the potential habitability of the many ice-covered ocean worlds we are discovering around other stars. Europa stands as the ultimate test case, a world of stunning contradictions where a deadly barrier might also be a lifeline, all under the watchful, turbulent eye of its giant parent planet. Solving this puzzle requires us to understand not just a moon, but the intricate and powerful interplay between it and the king of planets, a relationship that could either foster a second Genesis or guard a silent, watery vault. And so our journey through the 25 great mysteries of Jupiter brings us not to an end, but to a new beginning, a deeper appreciation for a world that is less a static planet and more a dynamic, breathing entity that constantly challenges the limits of our understanding. From the churning, ancient fury of the Great Red Spot to the silent, radioactive garden it might be cultivating on Europa, every layer of this gas giant reveals a new contradiction, a new defiance of our earthly expectations. We came with simple questions about weather and composition, and we found ourselves unraveling the very physics of matter under pressure, the chaotic birth of planetary systems, and the delicate balance between destruction and creation. Jupiter has taught us that a planet is not a simple orb in space. It is a complex system of interconnected forces, a cosmic engine where the deep interior speaks to the highest cloud tops, where the spin of the core dictates the fury of the storms, and where the invisible hand of magnetism sculpts environments of both utter sterility and profound potential. The most humbling lesson Jupiter offers is that every answer seems to reveal two new, more fascinating questions. Confirming the existence of a subsurface ocean on Europa immediately posed the puzzle of its chemistry and energy source. Mapping the planet's gravitational field to understand its interior instead revealed a shocking asymmetry that upended our models. Discovering the polar cyclones presented the serene order of their geometric arrangement, an order we cannot yet fully explain. This is the beautiful, relentless process of discovery, not a linear path to simple answers, but an expanding web of wonder that pushes the boundaries of science itself. Jupiter stands as a permanent reminder that the universe is far stranger, more dynamic, and more inventive than our neatest theories can often accommodate. It is a laboratory for extremes, a world that operates by rules we are still learning to write. The quest to understand this giant is far from over. It is driven forward by the next generation of missions already taking shape on drawing boards and in laboratories around the world. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, is now on its way to conduct a detailed investigation of Ganymede, Callisto, and Europa, seeking to characterize their hidden oceans. NASA Europa Clipper will follow, designed to swoop low over that icy moon's surface to determine the thickness of its shell, the salinity of its ocean, and the potential habitability of its depths. And beyond these, concepts for atmospheric probes that can dive even deeper into the clouds, or drones that could ride the jet streams, promise to bring back data from regimes we have only been able to guess at. These missions carry the next set of tools to probe these mysteries, and they will undoubtedly return with revelations we cannot yet imagine, alongside a new set of puzzles to captivate the next generation of scientists and stargazers. Now we turn the question over to you. After this tour of the King's greatest enigmas, which mystery captures your imagination the most? Does the thought of a vast, sloshing ocean of liquid metallic hydrogen fire your curiosity, or are you drawn to the haunting, geometric dance of the polar cyclones? Perhaps the potential for life in Europa's dark sea, a possibility both nurtured and threatened by Jupiter's radiation, is the puzzle you most want to see solved. Share your thoughts in the comments below. Let's continue this conversation about the most magnificent and complex planet in our solar neighborhood. The story of Jupiter is still being written, with every new observation, every daring mission, and every curious mind that looks up at that golden point of light and wonders what secrets it still holds.